Alright guys, in our previous video we took a look at mass spectra for really the very first time, and we looked at the molecule called pentane. So pentane was a 5-carbon chain, 1, 2, 3, 4, and 5, and then off of each one of these carbons we had enough hydrogens to fulfill the octet, or the 4-bond requirement for each carbon. So CH3, CH2, 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 and CH3. Now, what I want to do this time is maybe take a look at another molecule, just to give us a little more practice. And this is going to be 2-methyl butane. So let's draw this molecule out. 1, 2, 3, and 4, because buta means 4. On the second carbon, which is right here, we have a methyl group, so I'm going to put a carbon present, and we're going to load up all of these carbons with enough hydrogens to give us 4 bonds on each carbon. So this is the molecule that we've got. Now the reason I want to turn and look at this one is because I want you to compare the two structures. If I take the total number of carbons up here at the very top, 1, 2, 3, 4, 5. I have 5 of them. If I take the total number of carbons down here at the bottom, 1, 2, 3, 4, 5, I have 5 in total. If I look at the hydrogens, 3 and 3 is 6, 7, 8, 9, 10, 11, 12. And then if I take a look at the total hydrogens down here, 3, 6, 9, 10, 11, and one more makes 12. They're identical. The same number of carbons, the same number of hydrogens. They're isomers of each other, meaning that we have the same number of each atom, but they are connected in a different way. And what I'm seeing in that second choice is 2-methyl butane. Now the power of the mass spectrometer, how good is it? Well, if we do the formula weight up here at the very top, and we'll do a nominal formula weight, so 12 times 5 plus 12 times 1. Hydrogen weighs 1. There's 12 of them. That gives me a nominal of 72. So if this molecule stays together, I will see a 72 peak to show up on the spectrum. Well, guess what, folks? Same number of carbons, same number of hydrogens. So if this molecule stays together, I'm going to get a nominal weight of 72. Why is that important? Now, 72 here is the parent peak or the M peak in the spectrum. 72 here would also be the M peak of the spectrum. Now remember, in a previous video I told you, we cannot just look at M peaks to identify a compound. The fragmentation pattern is very important. This is why. 2 compounds, 2 different compounds, made up of the same number of carbons, the same number of hydrogens, which means that it has the same parent ion peak or molecular peak. Both of them will show a 72. But you know what both of them will not do? They will not have the same fragmentation pattern. Now, I'm not going to say they don't have the same fragments, right? We're looking at fragmentation pattern. That also takes into account abundance. Okay, so what does this mean? Well, let's take a look. Here's the mass spectrum of 2-methyl butane. I see the 72 peak. Right there it is. And it looks like the base peak here is 43. So this is the base peak. And we got to figure out, well, how does it get 43? Well, I can go back to my calculator if you forgot how we got the 43. And I'm just going to kind of randomly look at this compound and just start adding things up. So let's say that I get a fragment that's going to cleave right here. 12 and 3, 12 and 1, 12 and 3. There is my 43. So if my positive goes on this side, my base peak is coming from a CH3 hanging out here, and a CH3 over to the side. I just flipped it around on you. That's all that it did. But there's my base peak. Well, if that happens, then this 2-carbon piece, that's a 12 and a 12, which is 24, 25, 26, 27, 28, and 29. I now know where that 29 comes from. This is a CH2, CH3 with a positive. Okay. Now let's take a look at our other choices. I'm going to get rid of this split. I'm going to split it in a different way now. Let's cleave that methyl group off of there. What we're left with is maybe a positive charge right there. 12 and 12 is 24. Plus another 12 and 12. So 48. 49, 50, 51, 52, 53, 54, 55, 56, and 57. I now know how that 57 is showing up. This is coming from a CH3, a CH, a CH2, a CH3 with the positive right there. Then if I didn't give that side the positive, we'll erase it. And I give this side the positive. That gives me the 12 and 3, which is the 15 that sits down here below. Right? That's really the only options that I have to get some of these major fragments that are listed on the spectrum. So now you're thinking, well, it still doesn't make any sense. The same number of carbons, the same number of hydrogens gives me the same M peak that's down here at the end. And the molecule is going to fragment, but the molecule is fragmented in the same fragments. The 43 is still there, the 57 is still there, the 29 is still there, the 15 is still there. That's no different than what it was before. Yeah, there is a difference. Look at the height of the peaks. 43 is still the base peak, meaning that this molecule, if it fragments, is still going to prefer to fragment in this way. That is the most common thing that the detector sees. But look at your 57. This 57 is going to be much higher than the mass spectrum of pentane, which is what you're seeing here. Look at this, right? This 57 compared to the 43 is so much tinier in proportion to this scenario. 57 is going to be way higher in this case. Why? Let's talk about how the 57 got here. The 57 happened because we cleaved it at this spot, which means that this little bitty methyl group is going to go off on its own, and it's going to leave behind a positive charge on this big 4-carbon chain. That's where the 57 came from. If I take a look at this scenario, well, this is going to cleave off as well. This methyl group is still going to go off on its own, and we're left with a positive charge on that carbon. But the difference here is the carbon and the positive on it, the carbocation that got formed. Take a look at these two scenarios. This positive charge is attached to a carbon. When this goes away, we're left with a carbon that just has one more attached to it, and that's it. We call this a primary carbocation. For those of you in organic, you will appreciate that. Carbon, primary, only one other thing attached. However, in this scenario, when the methyl group leaves, we're left with this carbon that has two things attached. One to the left and one to the right. This is what we would call a secondary carbocation. Secondaries are more stable than primaries. And tertiaries, meaning carbons that have maybe three other things attached to it that has that positive charge on there, will be even more stable. You got to think of this as a drunk buddy in a club. All of these are the friends that go to the club with him. And this guy's drunk. The more friends he's got around him, well, they can prevent him from doing stupid things, hopefully. And because of that, it helps protect that carbon in the center. You protect your buddy. The more friends you have around you, the more eyes that you can basically be on you at all times, and that stupidness can be prevented. Same way with molecules. More friends, carbons, brought to the club in the molecule can help protect that carbon in the center from reacting. And stability is very important when it concerns a fragment. So this is a secondary carbocation. This is a primary carbocation. And out of the choices, this carbon's more exposed. It's got more chances to do stupid things in the club versus this one. That is why this 57 is higher. The molecule feels more comfortable cleaving it in that way. Even though it's not the most preferred way, it still is a little bit more okay with the idea of getting rid of that one little methyl group, that one carbon, and leaving behind this 4-carbon chain, because it is a secondary carbocation here. It feels more protected. It feels more trusted. Yes, I can trust you to go on your own, do what you need to do. You got some extra buddies that are going with you. Hopefully nothing stupid's going to happen. Here, it's a different story. If the molecule cleaves that one carbon and makes it go away, this carbon is more exposed. This carbon has more of a chance to go to the club and get in trouble, whatever you define trouble as, versus the other molecule. That is why this 57 is much lower, and that's why this 57 is much higher. So not only does the fragmentation pattern go by the weights of the fragment, but it also goes by the abundance of the fragment as well. That's how it determines the difference between pentane and 2-methyl butane. It looks at the heights of the peak, and it says, you know what? Compared to that 43 base peak, 57, this case, is going to be a little bit more dominant. It's going to show up a little bit more, and because of that, the abundance number matches 2-methyl butane more than it matches pentane. And the mass spectrometer will pick out that the molecule that you injected was 2-methyl butane based on that reason. So number one, it looks at fragment patterns. What pieces are actually there? And it narrows down the list. And it says, here are the handful that give us those fragments. And number two, it looks at abundance. It compares the heights of these fragments to the height of the base peak. How close is it? How abundant is it? And it uses these two to identify the compound that's at question. 2-methyl butane will fragment this way in this particular abundance amount. No other molecule will do the same fragmentation pattern with the same abundance. And because of that, the mass spectrometer is able to identify that particular compound. No standards are needed. You can go into it blinded, inject this sample, have no clue what it is, and like an infrared, it matches the database and it says this is the compound that you have. And this is why fragmentation pattern and abundance pattern, both of those are used to identify the molecule. So here we have an example question. And it says, what would distinguish the mass spectrum of 2,2-dimethylpropane from those of pentane and 2-methyl butane? Well, you know, this is not an organic chemistry class, so I probably would actually give you the structures here because we're just looking at how the molecules break up and how they fragment, right? I'm not really testing your knowledge of organic nomenclature. So I think that this question's somewhat unfair, but to play it fair, this did come from an organic textbook. That's typically where they introduce the concept of mass spectroscopy anyway. So I'm going to draw this molecule for you, 2,2-dimethylpropane. Propane means 3 carbons, so 1, 2, and 3. And on carbon number 2, I have a methyl group, so that is a CH3. And on carbon number 2 again, I have another methyl group. That's why the di is there, to represent 2 of them. So here is the molecule that we're playing around with now. Well, over here to the side, 1, 2, 3, 4. 4 times 12 is 48. And then the hydrogens, 3, 6, 9, and 12. If I add these up, and I get a total formula weight, and I actually did something stupid. This is actually 5 carbons. 4, 4, 4, 4 is 48, but we're having another 12. I can't forget that. So that's not really 48. This is actually 60. So 60 and 12 is 72. So this is the same M peak as before. There is no difference. So this is going to break down to how does the fragmentation pattern look. That's what this is all about. So we need to figure out how this molecule can break up into pieces. So we're just going to kind of do some trial and error here. So over here to the side, I'm going to start writing down some of the peaks that I would see. So I would see a 72 peak at least. All right, now we're going to kind of cleave this molecule, and I'm just going to kind of start here. So I'm going to break that bond right there. And what I have are 2 choices that could show up. I could put my positive on this side, and that would be 12 and 3, which is 15. We've always seen 15. It's present in the other 2. No big deal. I could also put my positive on this side, and I could add up this half of the molecule. So 12, 12, 12, and 12 is 48. 49, 50, 51, 52, 53, 54, 55, 56, and 57. So I would see a 57 that would show up. Well, we also saw 57s that showed up here as well, right? So that's not really going to be a difference as far as fragmentation pattern goes. Well, that's one way that I could go through and kind of cleave up this bond. Well, I could also kind of cleave it here. That would give me a 1 piece and a 4 carbon piece. That's no different, though, than what I just wrote down. So that's not going to make a difference. And then I'm going to cleave it here, and that would give me a 4 piece and a 1 piece. That's not going to make any difference either. And then I can come here and cleave it there, but you know what? You probably already guessed it. It's not going to make a difference there either. I get a 1 piece and a 4 carbon piece. And if I really take a look, that's my only choice. I can't draw more than one line. It's going to break up into 2 pieces. So there's no other way that I can draw a line here to get any other type of fragment. So how would you distinguish the mass spectrum of this? Well, my 15 and my 57 those are going to be pretty high because these are the only two fragments that I could really get from this molecule. I can't get anything else. So if I go back to the mass spectrum of the pentane, it showed me 29s and 15s. There's no way that I can get this anymore. Or not 15, but at least the 29s. The 29s and the 43s. I can't really get this anymore. There's no way that I can go through and pick this out or pick it apart and cleave it into two pieces where it will give me those numbers. The only option that I have is to give me a 15 and a 57. So I'm going to see a 72 peak, and I'll probably will find a 57 peak, and I'll probably find a 15 peak, but I won't find anything else. And that's a very good way to distinguish the difference between 2,2-dimethylpropane from the pentane molecule and the 2-methyl butane molecule that we've already looked at. I'm missing fragments here. And because of the fragmentation pattern, that's a no-ringer. I'll be able to pick that one out without a problem. The mass spec can at least. Versus something like these two where they have the same fragmentation pattern, the same pieces, they just come to me in different abundances. Well, here, I don't even have the same fragmentation pattern. I'm only seeing 57 and 15 to show up. There's no way that I can cleave this with one line into two pieces to give me anything other than the 15 and the 57. All right, here's another problem that we can maybe take away. What's the likeliest M to Z value for the base peak? There's the kicker. In the mass spectrum of 3-methylpentane. All right, so 1, 2, 3, 4, and 5. There's my pent. On carbon number 3 is a methyl group. And again, we'll give you probably this structure because some of you might not have had organic chemistry at this time, and that's okay. So I'm just going to fill in all the other hydrogens. And there's my molecule, 3-methylpentane. And it says, what's the base peak? So the base peak, again, is the most common, the most stable. That's not the M peak. That means when this thing cleaves, how is it going to cleave? Okay, well, I've got a couple of choices here. I'm going to draw these in different colors. So my first choice is to maybe cleave it here. And I'm going to see piece number 1, which is a carbon with 3 hydrogens, and then piece number 2, which is this whole big blob over here to the side. All right, my next option is that I can go through and cleave it here. This is option number 2. I get a 2-carbon piece to the left, and I get a 1, 2, 3, 4-carbon piece to the right. All right, my next option, I could cleave it here. I'll get 1 carbon, and then the 5 carbons that are left over. Not necessarily the same as in line red, though. And the reason is because this is a 1 carbon, yes. But this was not a straight chain 5 carbon piece. This was a 4 carbon piece with a carbon hanging out off the side. So that is a different type of fragment there. All right, then I move on. And I go to my next one. It looks like I can maybe cleave it here. What I have now is a 2-carbon piece and this 4-carbon piece. But you know what? This is the same as that purple one that I've just drawn, right? Because look, if I cleaved it here, I get a 2-carbon piece and the same 4-carbon piece on the other side. So that's actually already been taken care of. I don't even have to write down that option. I don't want to get you confused. I'm not even going to write it in the same color because that's not a choice. It just ends with the same thing. And then I can maybe cleave that end carbon, and that end carbon would be here. And I have a 1 carbon with a 1, 2, 3, 4, and 1 hanging off the side. But you know, we already did that one. That was the line red in the very beginning. 1 carbon chain, and then 1, 2, 3, 4 with 1 hanging off the side. So that's not really an option either. I'm going to get rid of that line. So down here at the very bottom, I'm going to write down our choices. If I use the red line and cleave it into 2 pieces, I could have an option of CH3 with the positive, or I could have the option of CH2, CH, CH2, CH3 with a CH3 hanging off and the positive piece going there. I now migrate to the purple line. That gave me 2 different pieces. I'll write those down. CH3, CH2, and my positive could go there. Well, the positive could also go on the other side. So this is CH, CH2, CH3, CH3, and my positive will just go there when that bond breaks. The next route is that blue line that you're seeing on the screen. Well, I could write the positive to this side and I get a CH3 all over again. Or I could write the positive on the other side. So CH3, CH2, CH, CH2, and CH3 with the positive at that location. So the question now is, which one of these will be the base peak? You start to see the problems with these questions now, right? Now, I know it's going to take a little bit of effort, but I always encourage you to write down the possibilities. Just write them down all on a sheet of paper and then begin to compare them. Which one of these is going to be the most common? Okay, well, here's the deal. I can kind of mark out some of these. I know that these small little pieces that have the positive charge, they're probably not going to be the base peak. All right? So that means that this methyl group is not going to be my base peak. This one's not going to be my base peak. There's other things that are here that are much larger to carry the positive charge. And I probably can cross out this one as well. Because again, there's other pieces that are a little bit bigger to carry that positive charge for me. That's one of the things that I look for. So I can kind of cross out half of these already, and I've got 3 choices to go by. They're all slightly different. So if I look at this piece, this positive is attached to a carbon that's attached to one other thing. This is a primary carbocation. This carbon is a carbon that's attached to 1 and 2 different things. This is a secondary carbocation. My other choice, this is a carbon. This carbon's attached to 1 here and to 1 there. This is a secondary carbocation. So out of the 2 choices, or the 3 choices that I have, I could probably rule out this one. And the reason is because this is a primary compared to a secondary that's here and a secondary that's there. So I'm narrowing the choices even more. Now, let's quickly go through and just assign some weights of these things. So this CH3 in the beginning, that's 12 and 3, which is 15. This one, I'm going to do that one too. Even though I've ruled these out, I'm still just going to do the weights just to kind of refresh that up, right? So carbon's 12 and 2, and then 12 and 1, and then 12 and 3, 12 and 2, and 12 and 3. This gives me a 71. Do the same thing down here at the bottom. 12 and 3, 12 and 1, 12 and 2, 12 and 3. This gives me a 57. And then finally over here to this side, This CH3, again, is going to be a 15. We've already done that one. And then I'm going to do that other piece. 12 and 3, 12 and 2, 12 and 1, 12 and 2, 12 and 3, which is a 71. Now, I've got this piece, which is secondary. That carries with it a 57 charge, 1, 2, 3, and 4. And I've got this secondary that carries with it a 71, a 1, 2, 3, 4, and 5. 5-carbon piece. So which one's the most common? How do I determine this? Well, they're both secondary. So I can't really use that as a guideline anymore to go by to figure out which one is my base peak. It helped me narrow down the choices, right? And this is what we do typically in the very beginning. We narrow down the choices until we get to a point where we can't really pick out which positive piece is going to be preferred. So here I have a positive that's a secondary carbon, and here I have a positive that's a secondary carbon. Stability-wise, not too much different. But there's two sides to every story. Those two sides basically mean that I need to look at the other half of the structure. That other half of the structure, two sides to every story. Again, carbon secondary, carbon secondary. I need to look at the pieces that I have marked out. Remember, I told you that in these cases, the molecule is going to prefer to break apart in the piece that it feels the most comfortable with. That it can really look at these pieces and say, I feel comfortable with you going out on your own. And the bigger the piece, the better. Well, in this scenario, if the molecule cleaves like it has, I get a 2-carbon piece and a 4-carbon piece. In this scenario, if the molecule cleaves like we've drawn it here, I have a 1-carbon piece and a 5-carbon piece. If the molecule has a choice, it's going to send them out with pairs. It's going to send them out with buddies. It doesn't like for this little CH3 to be alone. This thing is not very stable. Because statistics are going to tell me positive will go here, but sometimes positives will go there too. And the molecule is very reluctant to put those positive charges on those smaller pieces. And because of that, this scenario is going to be a much better case for the molecule. It gives a secondary carbocation which brings stability. And if it cleaves in this fashion, not only is this secondary, which is more stable really than the other fragments that we're seeing, with the exception of one, but the molecule says, you know, if I cleave in this way, I'm also relieving a CH2CH3 piece, which is bigger than the CH3 option in that case. And I feel better about my people going out together to the bar versus alone to the bar. Who knows what will happen to them? So this option is going to be better for the molecule. And if it has to choose, the molecule will cleave at that spot. Out of the two, the carbocation is going to be preferred to go with the bigger side, which means that 57 is going to be preferred. So which is the base peak? We're going to say 57. This piece does get generated. This piece becomes a negative if this gets to positive. This gets sucked out of the instrument. But, you know, just in case this does get the positive, it's going to show up, but it's got a buddy that can go with it, that CH2 group. It's not alone like it was in this scenario that would have happened. So if we go to the mass spectra of 3-methylpentane, that's exactly what we're going to see. Here we see the base peak right there. This line is happening right there's 55, 56, and 57. There we go. If I go back and take a look at some of these other ones that we've mentioned, we saw a 71 show up here, and we saw a 71 show up there. Well, on here, right there's my 71. There we go. That's why that's showing up. If I go back to the screen, I look at my other pieces. We had a 15 and a 15 that showed up there. All right, we go back to 15. There's 10. There's 15. Right there. It's kind of pitiful, isn't it? All right, we go back to the structure, and we start seeing some other numbers. We see this CH3CH2 group. I don't even think we did a formula weight for that one. All right, so 12 and 12 is 24, 25, 26, 27, 28, and 29. We would see a 29 here. I go back to the MS. At 29, we see it. Right there it is, 29. We now know what fragment gave that one. This was 57. We know what fragment gave that one. Now I'm going to go back, and I'm going to take a look at these other pieces, and that's really all the choices that we wrote down, with the exception of everything, right? So let's do the formula weight for the whole piece. All right, so I'm going to come up here. I'll do 12 and 3, 12 and 2, 12 and 1, 12 and 3, 12 and 2, 12 and 3. And this gives us 86. So on the mass spectra, there's 80, 81, 82, 83, 84, 85, and right there it is, 86. So we've identified quite a few of these, not every single one of them, right? Now, we also said that sometimes, you see that little bitty signal right there? That's a positive signal. There's a little signal right here, a little bitty one right there, a little bitty one right there, a little bitty one here. They're everywhere. Those are due to some isotopes that we're seeing. So we really can't go by those small ones. But out of some of the major ones, we really have identified quite a few of these. Well, we've not identified that one. And in the previous ones, we've not identified every one of those either, right? We kept saying there's some there that we're not going to worry about yet. We'll eventually get there, but just not yet. I don't want you to focus on those. So this is determining the base peak for a molecule. Think of how many minutes this caused. How many minutes did this problem take? This video is almost 40 minutes long, and we really only did one example problem. All right, so this is where I'm going to stop. In the next video, we'll pick up from here, and we'll keep trucking on, and we'll keep doing some more examples until we get comfortable of picking out where these most stable fragments are going to be.